finally, for Chapter 3, so far we've been looking at only one data at a time, only one variable at a time. But we may be interested in how two variables are related to each other. In this case, there are two descriptive measures we can use. They are called the so-called covariance and the correlation coefficient. The covariance is simply a measure of the linear association between two variables. So positive values indicate a positive relationship and negative indicates a negative relationship. So take two variables, x and y. If x has a positive covariance with y, that means that higher values of x tend to be associated with higher values of y, and low values of x tend to be associated with low values of y. In contrast, when there is a negative covariance, high values of x are associated with low values of y, and low values of x are associated with high values of y. These are the formulae for the sample covariance and the population covariance. The correlation is also a measure of linear association, but be careful, it doesn't mean causation. Just because two variables are highly correlated, it does not mean that one variable is the cause of the other. Try to think of some examples of these, and let's discuss them in class. And these are the two formulas for the correlation coefficient for samples and for populations. The correlation coefficient can take on a value between -1 and +1. So if values are near -1, that means there's a strong negative correlation. If values are near +1, there's a strong positive correlation. And if the correlation coefficient is close to 0, that means there's very little or weak correlation. So here's a simple example. Let's take 6 observations for the average driving distance and the average 18-hole score. Here is how we would calculate the covariance and the correlation coefficient. So, first, for each column, calculate the mean, 267 for distance and 70 for the score. For each column, subtract its respective mean from the data. Hence, 277.6 minus 267 is 10.65. 69 minus 70 is -1. Do this for each of the 6 rows. Then multiply this column by this. Hence 10.65 times -1 is -10.65. Minus 7.45 times 1 is -7.45. Add up everything in the last column and you'll get -35.4. Now take -35.4 and divide by 6 minus 1, which is the number of observations minus 1, and you'll get -7.08. That is also the covariance. Now remember from the previous slide, we also calculated the standard deviation of each variable, 8.2 in the case of the distance and 0.89 in the case of the score. Keep them in mind. Remember, we calculated the covariance, which is -7.08. Take that here and divide it by the product of the two standard deviations. and you'll get a sample correlation coefficient of minus 0.96. How would you interpret this value? What does it mean? Let's look at how to measure the distribution and its shape. If you remember from our first session, we looked at several graphs showing the distribution of data, and some of them are skewed, i.e., not everything is symmetric. Sometimes data will be skewed to the right or skewed to the left. There is a formula for calculating the skewness, and it's usually easily calculated by statistical software. We will not focus on calculating here, but let's do a review of what skewness means. So look at this graph. Look at the distribution. It's symmetric. The right side looks exactly the same as the left side. Hence, we say that its skewness is 0. As we will later see in the case of the normal distribution, this means that the mean and the median are equal. Now consider this. There is a tail on the left, and it's moderately skewed left, i.e. there's a tail but it's not all that long. In this case, when it's skewed to the left, we say that the skewness is negative, and the mean will usually be less than the median. Now look at this. There is a tail on the right, hence it's moderately skewed right. In this case, the skewness is positive. Look at this. It has a really long tail, hence it's highly skewed right, and the skewness is positive and usually has a value above 1. So again, let's look at the monthly apartment rent data. They've arranged it in ascending order. Let's look at the frequency distribution. How would you describe the skewness? To the right or to the left? Well, as you can see, there's a tail on the right, hence it's moderately skewed right. And as you will see, the skewness as measured is 0.92. It's high, but not above 1. Now remember, we said that the measure of location is the mean, and the mean indicates to us where the center is. The concept of the z-score, whose formula is given here, and which can easily be calculated by, for example, Excel. Well, the z-score gives us the following information. It tells us the relative location, because if the mean tells us where the center is, then the z-score will tell us for a certain value how far away is it, or how near is it to the center, which is the sample mean. Hence, if a value is exactly equal to the mean, then it will have a z-score of 0, because it's equal. And if a value is greater than the sample mean, then it will have a z-score that is positive or greater than 0. And if a value is less than the sample mean, then it will have a z-score less than 0. So again, look at the apartment rent data. What we do is for each value, we calculate its z-score. So take for instance 425. How do we get its z-score? Take 425, subtract the mean from it, which is 490.8, and divide by the standard deviation, 54.74. It gives you a z-score of minus 1.20. Why is the z-score negative for a value of 425? It's negative because it is less than the mean. And remember, values that are less than the mean will have z-scores greater than, will have z-scores less than 0. So as you will see, look at this lower right hand corner. Let's go back to that. That's the data for 615. Since 615 is greater than the mean, we predict that its z-score will be positive. And indeed it is. It's 2.27. And what's more, it has the largest z-score in the sample, which is not surprising because 615 is the largest value and therefore will be the farthest away from the mean. Why does this matter? Because most data, by observation and by assumption, follow a bell-shaped distribution, which is a symmetric distribution. We can then use the so-called empirical rule to determine how many data points, what percentage of the observations will be within a certain number less than or greater than the mean. We will cover this more fully in chapter 6. But for now, keep these three findings in mind. If data have a bell-shaped, then approximately 68% of the values of a normal random variable will be within plus or minus 1 standard deviation from the mean. Similarly, 95.44% will be within plus or minus 2 standard deviations from the mean. And 99.72% will be within plus or minus 3 standard deviations from the mean. This is also the illustration. As you will see, approximately 68% of the observations, that's the area under the curve and between 1 and minus 1 standard deviations. And this area will be between 2 and minus 2 standard deviations. And finally, all of this, which is 99.72%, will be between 3 and 3 standard deviations from the mean. Now remember extreme values? We also call them outliers. They are values that are extremely large or extremely small. So what we can already say here is if we have a data point and its z-score is less than minus 3 or greater than minus 3, then it's an outlier. Why do we say that? Let's go back to the graph. Look at this. If 99.7% of all observations are within 3 and minus 3 standard deviations, i.e. they have z-scores less than 3 and greater than minus 3, then if you have an observation whose z-score is like 5 or minus 7.2, then that means it's really very, very far to the left or very, very far to the right, i.e. they're greater than or smaller than 99.7% of the data, and therefore they're extreme observations. If you find outliers in your data, check carefully. It could be that the data was incorrectly recorded, a typographical error. Or it could be that the data value was incorrectly included. Or it could be that it really is correct and that there really is an extreme observation. That's the third possibility. Consider this again, the apartment rents. The lowest z-score is minus 1.2. The highest z-score is 2.27. 2.27 is less than 3, so it's not an outlier. Minus 1.2 is negative, but it's not as low as negative 3. Hence, it's also not an outlier.